Right, good morning. I'd like to give you a little bit of an introduction to automotive ECUs, the trends going on in the automotive industry, which is sort of a bit like buses, 3 coming along at once when you really need 1, and our response to that, which is the AURIX MultiCore product. So I'm not going to give you a lot of detail about MultiCore. On the assumption is you know what they are and why they're there. More about automotive and about the safety issues in putting an automotive system together. So, as you probably know, automobiles are no longer sort of the composition of mechanical systems. It's not just about metal bashing and getting an engine together. In 2008, around 10 million lines of code in the average premium vehicle. And just as may or may not be obvious, features usually come in at the premium level, get tried out, and then get worked out how to be cost reduced. Usually it's the electronics, not the software, that gets cost reduced. Into the medium range, and then goes into volume production in the low end. And software is responsible for about 80% of that innovation in premium vehicles. That's the inducement for you to go and sort of trade in every 3 years and buy a new S-Class or a Mercedes 7 Series. And it's now viewed that 30 to 40% of the added value in the automotive industry is based on software. Now, unfortunately, software has to run on something. Typically an ECU, electronic control unit. There are still some people using 8 bits out there. You don't need a lot of computing power to drive a seat, but it still is a controller there. So it's 8, 16, and 32 bits. And usually it ends up, some of the bigger ones look a little bit like that. That's one exploded. So they have a certain amount of mass and volume. And they consume a certain amount of power. There is now enough motivation for reducing CO2 with sort of potentially fines in the future if you don't hit the sort of 95 grams of CO2 per 100 kilometers, that there is actually enough interest in looking at the power consumed by those ECUs. So this is a very stylized and maybe difficult to see block diagram of where you would end up with ECUs and networks in a car, but it's got down to the point where people are hiding ECUs in seat rests, in the boot. Some are in gearboxes where the transmission fluid is used as a cooling medium. We've gone from sort of the first ECU in the late 70s to 43 in 2005 in a Passat, a mid-range model. Clearly in 2005 there'd be a lot more in an S-Class. 2010, around 70 ECUs. As I said, there's issues about the power being used by them. It's sort of in the fractions of grams of CO2, but that's worth money, and running out of room to fit them. A quote from Robert Rimkus of General Motors: there is no longer the room or the mass allowance to keep adding ECUs every time you add a function, so up integration, I guess that means integration to the rest of us, is now a requirement. So there's clear need for that integration to work. We need higher performance, both for adding and continued increase of functionality and also to get less ECUs in that car. So the trends that are coming together at the same time is MultiCore. I wouldn't be here at the MultiCore Challenge if that wasn't one of them. AUTOSAR as a software standard, and ISO 26262 as a safety standard. So clearly there's a need for more automotive performance. The sort of historical progression from 2002 through to 2010, we're based on faster uni-processors. The latest generation that we and our competitors are now putting out are 2 to 3 cores, so an effective megahertz of around 600 megahertz available to the designer. The question is, why have we gone multi-core and not just a higher performance uni-processor? Why not 600 megahertz? Clearly is not beyond the wit of man to produce a core that can do that. The issues in automotive are around power limitations and the memory issues. They're similar to the sort of reasons for going multi-core in other industries. They're just occurring at a much lower performance level for several reasons. One of them is heat and cooling. There's a strong drive for only passive cooling in automotive. If you need to put a fan in, that's a reliability issue as well as a cost. You want your car driving around in 15 to 20 years' time. The more fans in there, the less likely it is to be sort of still reliable at that point in time. We have a much higher leakage issue under the bonnet. 150 degrees junction temperature is the sort of working standard, and actually many times we're to have devices at a higher temperature than that. So 160 is not uncommon, and even beyond that. As I said, in transmission, the cooling oil isn't much below 160, so you take it as to whether you think that's cooling or not. And also, cost is very important. So anything that adds expense to the packaging, you know, having to use ceramic over plastic, having to use heat spreaders or not, these are all reasons to avoid cost, and as a consequence, we've gone multi-core at a much lower level. The other reason is the memory hierarchy. So on chip, we tend to have the complete memory hierarchy, and it's based on embedded flash. Embedded flash has scaled historically over past generations, but it's mainly been size reduction, and then it's allowing us to go up with capacity, but there's not been any improvement in latency. We're stuck, depending on which technology you're using, are either around the sort of 10, 20, or 30 nanoseconds. Nothing is going faster in embedded flash. And complicated memory hierarchies, level 2s, level 3s, shared level 2, shared level 3s, these are an anathema to hard real time. As Hank has just presented, you want to share as little as possible, so we can have multiple flash banks providing increased bandwidth. We just can't do anything about the latency. So a 1 gigahertz core would stall a lot more on a 30 nanosecond flash, so not much value in that. So as I said, multiprocessors with 2 to 3 cores in the 200, 300 megahertz operating frequency are common offerings from ourselves and our competitors. So it's a very similar technical problem that we're all facing and all ended up solving in a similar manner. AUTOSAR, great an acronym. It's an automotive open standard architecture. It's a modular software architecture, which may not seem necessary to sort of motivate that in the 21st century. But until very recently, a lot of automotive ECUs were based either on their own scheduler, proprietary AUTOSARs, and very little standardization. So if you were a OEM trying to take, say, an application and your goal being to reduce cost, to go from an ECU from supplier A to a $1 cheaper ECU on supplier B, there were no guarantees that you would actually end up saving any money by the time you'd gone through the porting exercise and the qualification exercise. So part of the goal of AUTOSAR is to bring in some standardized interfaces to allow both porting of software and composition of software, because there is a lot more integrated IP. As we've seen, we're trying to move from separated systems, a seat controller, a window lift controller. The IP will be from different players. If you need to move that onto the same ECU, you want to be using some sort of standard interface. So that's the sort of block diagram. It wouldn't look unfamiliar to anyone who's expecting sort of a layered approach to a structured RTOS. At the lowest level, you have very hardware-dependent layers, knowing about the microcontroller, layers knowing about the actual ECU board that the microcontroller is buried on, and then you have more standardized RTE, runtime executive, with well-defined APIs. However, if you thought this was a modern protected operating system to allow you to easily port code around, because of the legacy issue, there are scalability classes inside AUTOSAR, and the lowest level, scalability class 1, gives you a deterministic RTOS as a baseline, but it doesn't have any sort of protection. All of the code running on that ECU will be running in supervisor mode. As we see, as we move to look at some of the safety considerations, that is a bit of a challenge. There are more increasing scalability classes where there's protected timing, the expectation that there'll be a protected memory system, an MPU or an MMU in the system, and scalability class 4 promises both timing and memory protection. However, AUTOSAR is intended to span a range of cost points, and so it's not expecting that every ECU or every microcontroller will have an MMU. So there's or an MPU, there's quite a lot of 16-bit ECUs still being developed, not so many 8-bit. AUTOSAR was kicked off in 2003, been several releases during that time. Only in release 4 around 2009 was the sort of the implications that MultiCore was coming, was taken on board. and about the same time the sort of the implications of functional safety on top of the AUTOS. So there's quite a bit of difference between AUTOSAR 3 and AUTOSAR 4. As you can see from the diagram, there have been additional releases of Release 3, and that's because of the long lead times in automotive and the costs of porting and validation. Just because Release 4 has come along doesn't mean that your next release of an ECU is going to move to AUTOSAR 4. You're going to want to be continuing to develop small enhancements based on AUTOSAR 3. So we can sort of see that here in the growth of volumes of AUTOSAR. AUTOSAR 4, the yellow bar, is only just coming into use in 2014, and even there it's not necessarily on multi-core ECUs, it's still going to be on uniprocessor. And it's only as we go into sort of 2015, 2016 that we see that AUTOSAR 4 take-up is going to be higher than AUTOSAR 3. ISO 26262, the safety standard, it's an automotive-specific safety standard, and it's automotive restricted to, I think it's 4 wheels and less than 6 tons. So it means it doesn't apply to trucks and buses, and anyone who's riding a motorbike, you're on your own for safety. It's a development, it's sort of an adaptation and a standardization from the previous IEC 61508 standard. The ISO standard was published in 2011, so just, as I said, we're seeing these sort of trends come together at exactly the wrong time. MultiCore, AUTOSAR, and ISO 26262. If the automotive industry was just making one of these transformations at a time, it could probably cope with them more easily. Getting 3 of them at once has been a bit of a challenge. The standard takes into account some of the differences in the automotive, both supply chain from semiconductor suppliers to Tier 2, Tier 1s and OEMs, as well as the different operating environment. For an industrial control standard, the expectation is the machine is standing alone and it needs to be safe without an operator coming along and inspecting it every so often. In a car, there is the expectation that the driver at the wheel can have some control of things, of events when things go wrong. So, for example, a flat tire, it's expected that your average standard driver can steer himself off the road onto the hard shoulder in those sort of events. There are other things where there is no controllability. The worst case scenario for an airbag is that it goes off when you're not anywhere near an accident or running into anything. The driver, completely taken by surprise and then taken out of the steering equation, if he's been hit by it at force, is sort of the worst case scenario. So controllability varies in a lot of these operations, and those feed into the evaluation of the safety criticality. And there are 4 critical categories: ASIL A, which is the lowest, to ASIL D, the highest criticality. And there's an expectation that the additional code that has no safety category, just called QM, quality management. So in the system development, there's rigor specified for both hardware and software. There is an assumption that if the software has been developed to the required level, that it is then fault-free. This is clearly not any assumption that anyone who's had anything to do with software would make, but for mechanical engineers, it seemed like a reasonable idea at the time. But there is an expectation that the hardware will have faults. This will either be sort of wear-out mechanisms or random events such as soft errors. And if you want to run ASIL code of different levels, including quality managed code on the same ECU, this is possible, allowed for in the standard, provided it can be shown there is sufficient freedom of interference. And the expectation is that hardware will have fault rates, and they must be managed to a lower failure rate if the inherent fault rates are too high. The thing that the standard brings in is it requires a quantitative analysis. So previously using IEC standard that wasn't quite suited for automotive, you could get away with some qualitative assessments. ISO 26262 brings in the demand for some very quantitative analysis to get to prove that your resulting failure rates are lower than the requirement. So not quite sure how readable that table is, but it shows you there are sort of decreasing requirements as you go down from ASIL D to B. And the key point is for ASIL D, you need to show that with a particular technology fault rate, your system still doesn't have a failure rate that is greater than 1 in every 10 to the minus 8 operating hours, which is reasonably challenging. So that's the background environment in which we need to develop automotive microcontrollers, and AURIX is the name of a family of products that we've introduced recently into the market as a follow-on to our previous uniprocessor generation. AURIX as a family does go from continuing with uniprocessor members through to up to 3 cores, and there are dual core members in there as well. As it says in the sort of marketing slide, it's powered, not quite viewable from there, powered by TriCore and made for safety. So a little introduction to TriCore and a bit about the safety features that we've added. So TriCore is probably the most widely distributed microcontroller you've never heard of. It's in approximately 50% of all the automobiles produced this year. That's sort of the marketing average. It's probably not in 1 in every 2 cars, but there'll be a couple of microcontrollers in 1 in 3 cars. So it's probably about 40% of engine management controllers and probably on the order of 30% of sort of chassis and stability controllers. It's a 32-bit architecture. It's been around for about 15 years with a focus on hard real-time and combining RISC and DSP support for the sort of standard C and DSP data types you'd expect. And the application areas it's targeted: automotive powertrain, stability control systems, the advent of more electric vehicles, safety critical issues in regards to battery charging, so battery monitoring systems as well as the standard charging, and industrial control. So trains are another hard real-time safety environment, as well as things like turbine control and other industrial applications. I just want to give you first a high-level overview of what the sort of an AURIX family member would look like. This is one of the top-range devices with 3 cores. So the cores and the memory subsystem are located on a full-frequency 64-bit crossbar. There's a large number of very specialized peripherals for the automotive market. So while it does have an Ethernet sort of standard, there'll be lots of other communication protocols there you may not have heard of. CAN perhaps in the industrial control area, but FlexRay, LIN, CENT, PSI, these are very much automotive specialized. These are on a low-speed sort of 32-bit bus. And as well, as I said, a lot of the memory hierarchy is on chip. Very few of our devices actually support an external memory interface, usually at the high end for something like a truck application where the on-chip flash isn't enough to cope with the wide variety of emission standards. But for high-volume applications such as cars, typically the entire memory hierarchy is on chip. So it's embedded flash, around 8 megabytes is the current limit, and to be on-chip RAM. And we also do provide EEPROM emulation through additional flash. So safety features to try and meet the goals of ISO 26262. What is sort of obvious here is lockstep cores. You might not see in a multi-core processor in any other market. The reason for that is ISO 26262 is requirement that you deal with soft errors as well as sort of periodic checking for hard faults. So alpha particles in any sort of common silicon process will induce soft error rates that are higher than that 10 to the minus 8 operating hour requirement. It's high enough to violate that ACLD failure rate, so we need some mechanism to mitigate it. Now, there are clearly multiple approaches to dealing with soft errors. They're temporary. They just upset an upset at a specific time to a computation. You could consider time separation, spatial separation, or lockstepping your logic. Time separation, you'll run the task, the computation once. A little bit later, rerun the computation, and then in a third step, you'll compare the output of the 2 computations. This has the advantage of allowing you to scale the amount of safety you want. You only need to spend power on the duplicate computation when you require it. So if you've got some sort of mix of 50% safety, 50% non-safety, you don't need to spend extra power, which is what computation is, on the non-safety applications. Downside is it just about doubles your execution time. It doubles your resource requirements in terms of you need to have double the outputs, and depending on how you arrange it, maybe double the inputs available to be able to complete the computation with exactly the same values. It does have the advantages as a mechanism. It will scale from a single processor, uniprocessor member of a family through any larger numbers. And it gives you safety on demand. Spatial separation, if you have multiple cores, you can run the computation in parallel. You might be able to avoid duplicating your inputs, but you still have the problem of duplication of outputs, and you now need a compare function, probably run on one of those cores. If you had 3, you could run it entirely separately on a 3rd core, but you still have some increase in execution time for the compare function, and you have the resource requirements. The alternative is lockstepping the logic. This gives you very little increase in execution time. You're typically not holding up the computation to check for safety. It's an after the event indication that something went wrong, which for an automotive is sufficient to provide safety. Not the sort of thing you'd want necessarily if you were doing aerospace or aeronautical, but in a car, detecting a safety problem means you can typically go to a safe state. There's usually a safe state that says power off logic functions, and I'll have some default hardware function that allows me to steer off to the side of the road. The main reason for picking lockstepping as a solution to this problem is it gives you the simplest quantitative safety argument. If you take either time separation or spatial separation and then have a software compare function, you always have a very complicated interaction between hardware failure rates, a hard failure, something wore out just in the middle of the computation, as well as I've got a soft error event that may have occurred at the same time. You rarely have to deal with a case of 2 soft error events occurring either in time or on the separated cores, but it is a much harder problem to reason quantitatively about the flow of control that was taken by the task that did get the soft error event. If it just flips a low order bit of the program counter, such you linearly skip a couple of instructions, you may have missed out only a small part of the computation step, and you may happily get to the end of the computation having gone through most of the flow control paths. Doing that quantitatively is such a task that our evaluation was that it was a much easier solution to go with lockstepping. Here we're paying power for the safety, but we're only paying it on the CPU logic. We're not having to increase the extra, we're not spending duplicated RAMs, memory hierarchy, which is where quite a significant part of the power in a computation is going. As you'd expect, there's ECC both on the RAM and the flash. We spend a lot of time looking at the coding of both of those, the Hamming codes and the mechanisms there. So while it is only single error correct, double error detect, it also has a much higher percentage. We spend a lot of effort getting as high a percentage as possible of triple and 4-bit error detections, since that's what we require for safety. And the same thing with the flash, it's double error correct, triple error detect, with, again, a much higher percentage of 5- and 6-bit error detections. Not 100% guaranteed, you clearly can't get to that point without spending more ECC bits, but with the bits available, we spend effort on the encoding to try and improve the safety level. There's a transport check on everything going across the crossbar, and this is not just as simple as I put ECC on the address phase and I put ECC on the data phase. The other thing you need to be assured is when I went and asked for memory location 0, that I didn't get memory location 4 returned back with a very nicely formed data word and a very nicely formed ECC that matches the data from word 4. I need to know that I didn't get word 0. I've got a problem. Safe DMA, this does, as well as moving the data around, also computes on the fly in parallel CRCs on the address sequences and also on the data packet that got moved. Often the data packet might be new data coming in from a serial port, so you can't say much about knowing a priori what that is going to be. But if you move that packet around to other locations, you don't expect that value to change. So you can do on-the-fly checks that the packet that was originally formed has been moved correctly. And often, for address sequences, you are repetitively moving data from particular buffers to other buffers, you know what the address sequences will be. If a soft error strikes the DMA and it pickups on the address, the CRC won't match. So you've got some sort of confirmation that at least the regions that you are DMAing from and to have been correctly accessed. And in the right order, which is another slight problem you need to sort of show. For lots of the peripherals, there is some redundancy and they are spatially separated. So, for example, separate timers are very common, multiple SPI channels. We have bus protection for memory. What this means is that coming in from the interconnect, masters are checked to see that they are allowed to access the memory. That's done in memory ranges. We have the same thing for peripherals. That sort of level of system MPU is separate to the MPU inside the core, and the reason for that is safe interrupt processing and clock monitoring, sort of standard features. The reason for having a separate system MPU as opposed to a core MPU is that you may have running on a core QM code you can't necessarily trust to set up its MPU regions correctly. So it's up to the highest ASIL criticality software to go around, set up the system MPU, and then it can be locked down and not changed for the rest of the operation. So you can be pretty sure that if you've allocated a buffer of RAM to the ASIL D code, that none of the ASIL C or QM code can have modified any of the variables in that. As Hank mentioned, temporal isolation is more difficult than either sort of the spatial isolation. We provide the facilities with a crossbar and concurrent or parallel memory banks for totally non-interfering memory accesses. It does require the system designer, though, to make some concrete decisions. He needs to set up memories and deal with the fact that he can no longer share libraries. He's going to end up replicating them and copying them to different memories. What we're left with then as a source of timing interference or jitter is the peripheral bus. That is the single point that must be used by multiple of the real-time tasks. There we allow strict priority arbitration to be set up, so it is possible to bound the accesses for the most critical tasks and give you a very tight time bound. So you end up with a small timing interference effect. A quick, very quick. So custom migration, Continental took 700,000 lines of code. They went through training programmers up on the issues of multi-core, exhaustively identifying which of the variables are being shared and the use case points of those. They created their own tooling to allow, as tasks got mapped to different cores, that the copying in and out of buffers to be done automatically, and use some commercial tooling for the terms of the optimizing the placement and the data footprint that was going to be concomitant with those allocations of tasks to cores. So in 2013 they had a first working version on the multi-core device, and after a year of a bit more tuning they managed to, it doesn't work. So this is 2013, this is 2014. Now if you sum up the execution times here, they are actually very similar. What you get out of this more it's viewed as more optimized, is several nice characteristics. The actual peak execution frequency required by the entire task is lower, so if you chose to, you can dial down the frequency to reduce power. And what's very key is this green core here, for the tasks allocated to that lockstep core, are running what are known as angle-based tasks. So these are not time-based tasks, they're running on the red core. They're not necessarily interrupt peripheral driving processes. They're angle-based, which in an engine is a valuable resource. This is where you decide when to inject fuel, when to advance opening or closing of valves. So having as much headroom on that green core allows a lot more value added to be done in terms of trying to either increase performance or control emissions. So while this may not have actually reduced total load on the core, it's enabled on the microcontroller, it's enabled a lot more value added to be put in later on a key resource. Thank you for your attention.